independent versus dependent events. What do you think of when you hear the word independent? Someone's independent. They don't depend on anyone else. What do you think of when someone's independent? Alone. Single. Okay. Now that's kind of depressing. Independent. So,
they can do it by themselves.
all but do it by themselves. Very good. So, independent is when one event does not affect another event. The first event does not affect the second event. So, if I toss this coin,
You got it.
ooh, I did all of it until it got on my hand and then it slipped off. So I got tails. Does what I got that time, does me getting tails affect what I'm going to get this next time?
No.
Has nothing to do with what I get that time. Tails again. So tossing a coin multiple times is independent. Something that is dependent is when you have a bag of M&Ms. You've got your bag of M&Ms and you choose an M&M out and you eat it. Is that going to affect the probability of the next one that you choose out of the bag?
Yes.
It will, because now there's one less M&M in the bag. It is being digested in your stomach. It's not in the bag anymore. And so it does depend on which color you chose first, the probability of drawing the next color. Okay? Independent, dependent. Someone name another probability that would be independent. Can you think of something? A spinner. You can spin that spinner as many times as you want, but spin number 1 is going to have nothing to do with spin number 2. Nothing to do. Very good. Very good, Kendall. So spinner. What else? Give me one that is dependent. Give me another one that's dependent, someone other than Kendall. No. Give me one that's dependent, someone other than Kendall.
Dice.
Dice is dependent?
No.
Okay.
Wait, see?
I want you to name a probability that is not M&Ms or any sort of candy that is dependent. No.
Marbles, when you're picking marbles.
Picking marbles? Okay, okay.
You
So you're
said
still
no
picking
candy.
something, no candy, okay.
Sure.
So if you pick a marble from the bag, but you need to be specific, you pick a marble and you don't replace it. Because if you pick a marble and you replace it, it's independent. But if you don't replace it, if you keep it over here, then it's totally dependent. All right, let's go to this slide. I have 1, 2, 3, 4 situations. I need 4 students, and you're going to read the situation, and then you're either going to put independent or you're going to decide that it's dependent. Who would like to be my first guinea pig?
Oh my God. Sure. Sorry.
I'll use my cards. I'll call on someone.
Watch it.
I want to be.
Megan,
Are you kidding me?
pick a situation and drag it to the independent or the dependent column. You get to pick any one you want. You get the pick of the litter. Read it out loud. You've never heard that phrase, the pick of the litter?
Yes, I have.
Like when you go, you're gonna buy a cat, and you're the first one there, so you get to pick any cat you want. Okay, go, Megan, go.
Picking a red,
Shh. Megan is reading a situation out loud.
yeah. Taking a red, then a blue, then white sock from a drawer to pack in a suitcase.
Sweet.
She
Suitcase.
said it normal. Okay, is that dependent or independent?
Dependent.
Drag it to the column. Awesome, very good. Yay! So why is that dependent?
Because you're not replacing it.
Because you're not replacing it. Very good. You've got a drawer full of socks. You pick a red. Now what's the probability you're going to pick another red? That red's gone from your drawer. I don't know how many reds you have in your drawer. But anyways, because you're not replacing it, because you're putting it in a suitcase, it is dependent. All right, Nasia, you're up.
Go name that.
Read it out loud first, whichever one you're choosing.
Selecting two-face cards when the first card is replaced.
Very good. Yay! Independent because, what's the key word?
Replace.
It is replaced. If you put it back, you have started the experiment all over. You have reset the experiment. Yes, ma'am. Yes, you know. Absolutely. Kendall, you're up. Should have got my iPad out so I could bring it to you so you wouldn't have to walk all the way to the board from the back of the room where you chose your seat. All right, go ahead and start reading it while you're moseying up to the board. Can you read out loud? So the class can hear. You might not be able to see it from the back.
Selecting a white bead, not replacing it, and then selecting a red bead.
Thank you. Oh, she's not here. Sorry. Try again in a minute. Not replacing it. Not replacing it. So it's automatically dependent because it is now out of the bag. Very good. Last one's Brett. Read it out loud.
The probability that Sarah will get a blue gumball after Chris and Mario got green ones.
Who's ever gotten a gumball out of a gumball machine? When you get a gumball out, do you put it back after you get it out?
I do. I do.
Stop playing devil's advocate first, Perry. When you get a gumball out of the gumball machine, you put it in your mouth and you eat it. You don't put it back in the gumball machine. So that means you are not replacing it. So where should this one go? It's okay. You don't have to be sorry. There was no spot for it. It was tricky because there was no spot for it. Because you don't replace gumballs back into gumball machines, it is dependent. Because as soon as, let's say there's 5 blue gumballs. Sarah gets a blue one. Is the probability of getting a blue one different now? Yeah, because now there's only 4 blue gumballs. We've talked about that long enough. Example number 1, on your notes, follow with me. Do it in your calculator if you don't know where your notes page is. Example 1, what's the probability of flipping a coin, landing on tails, and then rolling a 4 on the die? Are those independent or dependent? Those two events.
Independent.
Very good. The coin is not going to affect the die. The die is not going to affect the coin. Those are independent events. Let's start with Melanie. What is the probability that the coin will land on tails? 1/2. Very good. Omar, what's the probability that we roll 4? 1/6. So what do I do with those? Add, subtract, multiply, divide? When you want 2 events to occur, you multiply them every time. When you want 2 events to occur, you multiply them. 1/2 times 1/6. Guys, it's just 2 times 6. What are you doing? Stop going to your calculator. What's 2 times 6? 12. 1 times 1 is 1. 2 times 6 is 12. You need to be able to go back and forth between fraction and percent. Matt, what is 1/12 as a percent? Now you're allowed to go to your calculator. 1 divided by 12, and then you move the decimal over twice. 8.3%. So that's a small chance because that's out of 100. There's an 8.3% chance that we will land on tails and we will roll a 4. So John, come on up here and you're going to see if you can defy the odds. Can you land on tails and roll 4? You only have an 8% chance of doing it. Here you go. You can let it land on the floor or you can catch it. Doesn't matter to me.
I'll check that in a second.
What do we get? I don't know. This is nickel. I don't know the difference. Oh, you got heads. Anyways, let's roll the die just in case. Let's see if you can get yourself a 4. What'd you get?
I got a 1.
A 1. Well, he fit the probability.
Someone else do it.
There was a 92% chance that he was going to fail. A 92% chance. So it makes sense that he failed. Okay, Austin just volunteered himself. He wants to try to defy the odds. Try to defy. Oh my
That
God.
was terrible.
That was pretty terrible. Oh my gosh, you're going to make me come all the way down here. And you got heads. Go ahead. Let's see if you can get half of it right.
See if you can get 4.
1! They rolled the exact same thing! You want to try, Kendall? Is that what you were using? Yeah? Okay, last one. 92% chance of failing.
What if he gets the same as me and John?
He's gonna get a tear.
Yeah, what's the probability that both of them got?
Oh,
Oh, you got your tails! You're halfway done.
He's got it. He's got it.
Oh, goodness. 3. He was 1 off. Okay. No, guys. It's not bad to fail at that because you have a 92% chance of failing. Next example. What's the probability of selecting a card that's a heart and then selecting a card that is black without replacement from a standard deck of cards? Dependent or independent? Good job. It is dependent because of that phrase right there. It is dependent. What you do the first time depends, well, it doesn't, what you do the second time depends on what you do the first time. Torin, let's do these one at a time. What is the probability that you select a heart? Let's start with this. How many cards are in a deck? 52. How many of those cards are hearts? 13. Very good. 13 out of 52. You should be writing this down on your page. Because some of you might not have ever played with cards growing up, and that's fine. There are 13 of each suit. There are 52 cards. Julius, Torin is holding the heart in her hand. She's holding it, so it's not in the deck anymore. How many cards are in her deck now? Julius? 51. And what is the probability that you draw black? What? What? Okay, how many black cards are in the deck? 26. Is there a black card in her hand?
No.
She drew a heart. Hearts are red. So how many blacks are still in there? 26. 26 because she has a red one in her hand. Please multiply those. I do not recommend doing this one by hand. I do recommend using the calculator. And then you need to do math, enter, enter when you're done pressing all those buttons. Shelby's not here. Kaylee's not here. Louis C., tell me what you get. Yep, 26 divided by 1. Enter, math, enter, enter. Yep. 13 over 102. Louis, what is that as a percent? Look at that decimal that you had. Oh, okay, good. Just move it over twice. 12.7. So, we're going to do this experiment, and Torin and Julius have a 12.7% chance of success. So what's their chance of failing? 80. 87.3% chance of failing. Okay, Torin, here we go. Draw us a heart. She got a heart! Oh my gosh! Now you have to get a black card. You have to get black. Or you fail. You have to get black.
He's gonna fail it.
Yeah.
50-50 chance pretty much of getting a black card.
Get a black one.
Yes!
It's
It's a tiny bit. They've success! Heart and black. Wow! Good job. Nice work. That was fun. Okay, next one. Now we're going to use a table. We're going to use a table of data to make sure that you can interpret this. In 2004, what county do we live in, by the way? Harris. We are in Harris County. In 2004, what's the probability that someone voted for Bush given that they were from our county? You have the table on your paper, so I want you to see what you come up with by yourself. For those of you who couldn't find their notes, I'll make it a little bit larger.
Do we have to like add them all together?
In the denominator, you always put totals. So yes, you would have to add something together. This is really important right here. Given that they were from our county. So you are only counting people who are from Harris County. You are ignoring the rest of the people on the table. Because they are for sure, they have to be from our county. So you should not be looking at those numbers right there.
Why does it say 1,000?
These 580 people, 581 people did not vote for Bush. 581,000 people voted for Bush. They didn't want to crowd the table with all those zeros. So these are the numbers in thousands. Does that make sense?
Wait, how many people voted for
I don't know. But this is how many people voted. You need to add up these. This is how many people voted. So, Catherine, what's our total? Did you add up 581 plus 472 plus 5? What'd you get? 1,058? Okay. So our total, that's what always goes in the denominator, is 1,058. Alea, how many people voted for Bush? 581. And Alea, tell me if that can be reduced. So 581 divided by 1,058. Math, enter. Nope. Okay, now give it to me as a percent. So you take the decimal and you move it over twice. 54.9%. So 55% of people from our county voted for Bush. So over half the people. The probability that you grab someone and they voted for Bush, you have over 50% chance that they voted for Bush in 2004. We are almost done. Give you a slight challenge problem. All right, we've got a spinner. How many numbers are on our spinner? 8 numbers. We're going to spin the spinner twice in a row. What's the probability? The sum, what does sum mean?
Total.
Add. It means add. What is the probability the sum is less than 6 and the second spin is a 2? Whoa! Let's see what you can come up with. Use those brain cells. The sum is less than 6 and the second spin is a 2. It is a 2. I'll give you a hint. You need to start with the second spin. Don't start with the first spin. Start with the second spin. That's my hint. There's my hint. The second spin is for sure a 2. What's the probability you spin a 2? It's 1 out of 8. You are going to multiply, but you have to find that first one first. Oh, good. Okay. So if the second spin is for sure a 2, what numbers could you add to 2 and still stay less than 6? Which numbers would be favorable?
3, 2.
Well, how about, let's start here. 1, 2, and 3. What if I spun a 4? What's 4 plus 2? Is 6 less than 6? No. So there are 3 favorable outcomes for this first one. There's 3 that we want to spin. How many total numbers are there on the spinner? 8. There's still 8. The number of numbers on the spinner does not change. So this one was a little bit difficult. We had to do the second one first. Then we had to see which numbers combine to be less than 6. Now we just multiply them. 3 times 1 is 3. 8 times 8, 64. Can that be reduced? Math, enter. Nope. What is it as a percent?
How do you find the percent?
Yeah.
Okay, do 3 divided by 64. And then you can either multiply it by 100 or percenter.
4.6.
Or you can just move the decimal place over twice.
4.7
Move it 1, 2, 4.687. So Kendall was saying 4.7% chance. Very small chance that you spin it twice and it's less than 6 and the second one's a 2. Okay.